All right, so let's continue on. And let's look at the set of real numbers and their properties and how those properties are used. So we're going to consider a set of numbers, and then we're going to list the possible numbers they might be. So I guess the first thing I need to do here is, well, what possible sets of numbers do we have? And so your book does this with natural numbers, whole numbers, and I'll use these double type symbols, integers, rational numbers, irrational numbers, and real numbers. And so those are the possible set a numbers can be in. And so what we're going to do is we're going to grab a set of numbers here. I'm going to try to stick with the examples here. So give me a second to write these over. -7, -3/4, 0.0, 0.6 repeating, square root of 5, our friend pi, 7.3, and the square root of 81. And so we'll look at all these numbers and we'll try to figure out what set they belong to, what sets they belong to, I guess I should say. My English is a bit odd today. I will try to speak more proper. And so if we look at these numbers, I don't see any natural numbers right off the bat. But if we look at this one, that's probably better written as 9. And so the square root of 81 is a natural number. Now for whole numbers, we get natural numbers plus 0. So we'll get 0 and square root of 81. The integers, well, that's going to be negative numbers, 0 and square root of 81. So see how square root of 81 is belonging to the other sets of numbers that we're building from. And now we need to look at rational numbers, numbers that can be written as a fraction. So -7 can be written as -7/1. -3/4 is a fraction. 0 is a fraction. 0.6 repeating is a fraction. Square root of 5, well, that's not a perfect square, so I can't do anything with that. Pi isn't, but 7.3 I can write as 73 tenths, and square root of 81. And so the rational numbers are pretty big here. Now for our irrational numbers, well, that's square root of 5 and pi. And then the real numbers, I don't even have to rewrite them, it's all of these. And so there we've classified the sets of numbers that these can be. All right. Oops, let me move over here. Okay, so we can classify numbers based off of these categories we used. Well, why is that useful? Well, what we're going to find is different types of numbers get used in different ways. When we count, that gap in the middle isn't really needed. But when we measure things, right, and we don't quite get to an exact number, we need to find out what's in between the numbers. And we do certain manipulations, like with circles, we will need these irrational numbers to come into play. And so these different types of numbers have different usage, especially in statistics. Well, more than just statistics, the difference between a counting number and a real number, right, all those infinite ones in there, determine the probability of something. And if I have things I can count, it's easy to say I have 1 out of 3 chance of something. But if I have this infinite amount of things, I have to treat the number differently. And so this classification scheme, even though it seems kind of odd, why don't we just use real numbers and the properties of real numbers for everything, isn't how we always use a number. And so if we're going to use the idea that mathematics is a language, when we use a particular part of it for use, we have to use it in that context. And one of the other things we have to realize is numbers get double used, right? Because we built up from these, the idea of this square root of 81 being able to be used in any one of these contexts is appropriate for the type of numbers, and sometimes transparent. Sometimes we don't even recognize that we're doing it that way. Let's continue our exploration of real numbers, and we're now going to put all of the properties of real numbers together. And so we're just going to look at some of the properties of real numbers. Right? So 3 times the square root of 7 is equal to the square root of 7 times 3. I don't know. I think I can do better than that. That's the one the book uses. Let's actually look at 2 times 3 is equal to 3 times 2. This shows us, because we know from memorizing our little multiplication tables, that 6 is equal to 6. Doesn't matter what order I multiplied to get to it. Let's look at association. 4 plus 7 plus 6 is equal to 4 plus 7 plus 6. Well, let's do this. I'm going to switch colors here because orange is bugging me. So I get 11 plus 6 is equal to 4 plus 13, or 17 is equal to 17. That's kind of neat, but let's kind of think what happens. If I'm adding 4, and I'm going to add to it 7, and then I'm going to add to it 6, and so I'm saying I'm adding all of these things. Well, if I add these first, I get this, right? But hey, if I add these two first, well, I still get the same thing. And that's what the associative property is really doing, is we're collecting our tick boxes, right? Our ticks, but our hash marks, our tally marks. But these represent numbers. Of course, I have to have them represent the right numbers. So let's point them back. This is the 4, this is my 7, and we'll shoot you around in here, and that's my 6. And so this is a property because addition represents this grouping and how these groupings come together. All right, so the property of numbers aren't too bad. Well, let's look at another property of real numbers, one I like to use a lot. Right, 2 times 3 is 6, plus 10, which is 16. But that's this. Whoops, I did it. Let's do it both ways. Let's look at commutation. That's saying the same as 2 times 3 plus 2 times 5, which is 6 plus 10, which is 16. But that's the same as saying 2 times 8, because I'll add what's in the parentheses first, is 16. Now notice, if you ever talk about the order of operations, it doesn't seem like I'm doing the order of operations here. But the thing I'm doing first is I've transferred it to something else, right? I'm not doing my multiplication first. I'm changing it into something else, taking care of my parentheses before. So don't think this violates the order of operations or changes where the order of operations came from. It's just a way of saying these two things are like, so we can use either or. And algebraically, we'll find places where this is very helpful for us to pull things together or to separate them apart, because it changes the pattern we are looking at. All right, one of the things that that the book brings into right now, and it's interesting because this gets developed, is not all numbers go to infinity. There are number types that we'll eventually study that deal with the idea of rotational symmetry. That I can rotate around the circle, and if I rotate exactly m times around, I'm always back at the same place. And rotational symmetry is how we are going to describe that. And so we say it takes m terms to reach back to the same place. Well, that means if we divide something like a clock, let's say, into equal numbers of 5, well, 6, this has 6 numbers in it, right, including the 0, then I can do what's called clock addition, and I can add by these numbers. So 1 plus 0 is 1. 2 plus 0 is 2. Right? I can add by anything in the clock. And what's neat is I can get things like, well, 3 plus 3, well, what happens? I go 1, 2, 3 is 0. And 3, whoops, put my circle around the wrong thing. 3 plus 4, well, 1, 2, 3, 4 brings me to 1. There's this idea of rotation that comes about in clock symmetry. Later on, we'll say that things that do, functions that do this or things that move through this are periodic. But this type of symmetry and this returning to numbers does happen in nature. We have things that are trapped within their processes. We have things that rotate. And so this is not a bad way of doing it, but we have to say, hey, this is different addition. And so we put a circle around it to say we're going to do clock addition. And it's like adding the hours on a clock, which means for the number of hands, for the number of spaces we have a different addition table. So for this particular table, we get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so 0 plus 0 is 0. Right? Zeros give you the same thing back. So I'll write these down here. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 0, because I've rotated back. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. 2 plus 4 is 0. And 2 plus 5 is 1. 3 plus 1 is 4. 3 plus 2 is 5. 3 plus 3 is 0. 3 plus 4 is 1. And 3 plus 5 is 2. Because 3 plus 5, 1, 2, 3, 4, 5. 4 plus 1 is 5. 4 plus 2 is 0. 4 plus 3 is 1. 4 plus 4 is 2. And 4 plus 5 is 3. Right? 4 plus 2, 1, 2. 4 plus 3, 1, 2, 3. 5 plus 1 is 0. And notice how the zeros make a diagonal through here. And everything starts repeating again. And then 5 plus 2 is 1. 5 plus 3 is 2. 5 plus 4 is 3. And 5 plus 5 is 4. And so we have an addition table on this, what we call clock addition. And because of the closure property, any addition within our clock system has to work. But what we want to see is if our other properties work with clock addition. So if this is our addition table, then we do have closure because we limit ourselves to our clock set. And in this case, our clock set is going to have 6 digits or 5 numbers. And of course, we could make more numbers in our clock set. We could increase or decrease. And so let's verify identity. Let's see if the distributed property holds within clock addition. And so let's take, whoops, that's the distributive. Let me start easier with associative. Let's make sure associative addition works. So A plus B plus C is equal to A plus B plus C. So 2 plus 3 plus 4 will be the example we use. 2 plus 3 plus 4 is equal to 2 plus 3 plus 4. Now using our new addition table, 2 plus 3 is 5. And 5 plus 4 is 3. And let's see, 3 plus 4, so 3 plus 4 is 1. And 2 plus 1 is 3. So it appears our associative property does work. That's nice. And so what is our identity element? Right? What do we add to a number in, right, identity? Well, notice it's 0, because if I add 0 to any number, I get that number back. And so clock-like addition holds the identity property. But the inverse property, right, our inverses are not as transparent as they were before. And so the inverse says A plus some other number, and we said negative A in other numbers, but we don't have the idea of negatives here. So I'm just going to call this, I want to use a Greek chi equals 0. Some number plus the inverse is equal to 0. Well, let's look what we need looking through here. So if I take 0, what number do I have to get 0 back? So I take 0. What number do I add to get 0 back? Well, it's 0. If I have 1, what number do I need to get 0 back? Oops, over here. And so if I have 1, what number do I need to get 0 back? I need 5. And if I have 2, what number do I need to get 0 back? Well, I need 4. And if I have 3, what number do I need to get 0 back? 3 again. And if I have 4, what number do I need to get 0 back? 2. And if I have 5, what number do I need to get 0 back? Well, that's 1. And so our clock numbers do take on inverses. And let's see what happens. So do they commute? So A plus B, does it equal B plus A? Let's look at both sides of this table here. Let's do again, I want to try to keep the same examples as the book. So I'm going to take 3 plus 3. 3 plus 4, I'm sorry. Clock addition, 3 plus 4. Make sure these are all clock additions. I forgot my little circles here. And does that equal 4 plus 3? So I come down, 3 plus 4 is 1. And now I come over here, 4 plus 3. Hey, it's 1. All right, let's look at another example. Five clock addition 4, 4 clock addition 5. So 5 clock addition 4 is 3, and 4 clock addition 5 is 3. Right? Notice I'm going in both orders. Because this clock has this backwards and forward, I'm checking this side plus this side, and this side plus this side to make sure commutation works. And 3, and so let's also verify them on the other side. So 3 plus 4, 3 plus 4. It works in both directions here also. 5 plus 4, 5 plus 4, 5 plus 4. So it works in both directions. 4 plus 5, 4 plus 5. And that's that diagonal striping in these that we're seeing going on, is the directional striping. And so clock addition satisfies the rules and properties of real numbers that we have been looking at. All right, until again.